Swayam Prabha. Digital India. Educated India.
Okay, welcome to this lecture series on basic surveying. Now today we are on module 9, which is about computation and adjustment, and we will be talking about the lecture number 2. In this we will be covering, as you can see here, again the concept of the least square, then how do we define the least square, then we will be looking into the redundancy of a model. What is the redundancy? Why do we need it? How to plan for it? How to compute it? Then the adjustment can be carried out by two methods, like condition equation method and observation equation method. There are other methods also, but we will be basically concentrating on these methods. So we'll start about these methods today. Now next, we'll start with again the concept of the least square. We have done it in the last lecture also, but again to revisit. For example, let us say we have a line and we want to take the measurement of line. So what we can do, as we can see here in the slide, over here this is the line and this line is to be observed. We can do two things. We can go for only one set, means we take only one observation, and the second set we can take 3 observations. So the same line is being measured 3 times. Now what is desired here? The desired is the estimate of this line, or we want to know what is the length or the estimate of this line, which is the best estimate from our available data. How do we proceed? Okay, in the first set we have taken only x1, and what we know, if you are taking only x1, well, our solution will be unique, means our estimated value is equal to x1. Only one observation we have taken. We just observed it once, so we can't say anything else about that length of the line except that observation. So our estimate of that observation, or we can say adjusted value, the final value, is equal to the observation. But this is not desirable, as we have seen, because we do not know how much error was there in that one observation, and whatever is the error amount, we are going to take it. We don't have any check. So this is not desirable. Now in set 2 we are going to observe the same line 3 times. Now this is very much desirable, because if in x3 there is some error, the chances are in x1 and x2 the error will be less. The errors are always there, but we have a way to check for the errors, for huge amount of errors, as well as we are carrying out multiple observations, so that we have more set of data. The redundancy is there, and this redundancy is very much desirable whenever we do surveying or any observation. But the problem in this case is how to determine the desired. Our desired age estimate or the length of that line, but we have now 3 set observations, x1, x2 and x3. Out of these 3, which one, or average of all these 3, or average of any 2 of these? So what we see, we have now many possible solutions. So if I write all these possible solutions, the solutions could be, well, any one of these observations, the estimate is equal to any one of these observations, or maybe average, as you can see here, estimate is average of first 2 observations. Similarly here and here, or maybe average of all 3 observations. So what we end up with? We end up with a situation where if we are not applying a proper technique, we end up with a problem that out of all these possible solutions, which one is the right solution? Which one should we take? We should have a way to say that. Now, to answer this question, we will go for the technique of the least square. Because there in the ground is one physical line. It has a length between 2 points. It can't have multiple lengths or multiple estimates, as we are seeing in the previous slide. It's one line, so it should have only one value. So what we will try to do, making use of all these observations which are desirable, because we want to have redundancy in the observations, we will try to estimate the best possible solution for that line or best possible length. Okay? How to do that? So we are looking for a technique which gives a unique estimate, obviously. Now this estimate should be the best under given conditions. Further, the techniques should account for relative quality of observations. Now this is also very important. We know about that stochastic model. Okay, depending, we took 3 observations, x1, x2 and x3. If we have some idea about the precision of these observations, the weight that we can give to these observations, we should take that weight also into account. If we know x3 was observed when the weather was very poor, and it was very difficult to observe in the field, but still we have an observation x3. So what we would like to do, we would like to give x1 and x2 more weight and x3 less weight. So we should have some method of giving weights, and these weights should be accounted for when we are computing the final estimate out of our adjustment process. So this entire thing, all these can be realized by least square, and we have already seen how do we write the least square. The sum of square of residuals, we can take the weights also into account, should be minimum. We have seen that also by using a line fitting example. We wanted to make, or the best fitting line was the one for which, or rather which deviates least from all the sets of points, all the points there. That's the best solution, which deviates least in overall sense, and that can be done by the least square. Now what is this criterion of the least square? How do we actually do it? So what we'll do, we'll assume L, let us say, is a vector of observations, anything. It could be the observation for a line. There is a line and we are observing the length of this line, okay, x, x1, x2, x3. So L is the vector of observations. We have taken 10, 20, 30, 100, whatever number of observations. Next, we take V as the vector of residuals. We know what the residuals are. If in observation I add the residual, we get the estimate. Okay, L is the vector of estimates, and they are related like this, that L hat is equal to L plus V, as we were saying. If we add residual to the observation, we get the estimate. Now this estimate should be consistent with our model. We have seen now that our observations should satisfy some model. Okay, we have seen those geometric conditions, observation conditions, we have seen those. So our observations should satisfy those. So by the least square approach, what we will do, we will try to find the estimates which will also be consistent with our model. In addition, we already know that we should take into account the stochastic model, where we account for it by the weight matrix. Now over here, how do we decide the weight? There are various criterion. One of them is that the weight is inversely proportional to the variance. Okay, in any observation, we are taking, for example, let's say for length. a length is being observed and it has been observed, let's say, n number of times. Now the other day also the same length was observed, x, and again observed, let's say, n number of times. This was observed by a person A, this was observed by a person B. Now out of two sets of these observations, what we can do, we can find the mean, we can find the variance, okay, standard deviation, and more is the standard deviation of these observations. What is the meaning of it? They deviate more from the mean. So the deviation of the observation, the variance is more. So that means the precision of the observation is less. So if the precision is less, we would like to give less weight to the observation. So because of this only, we know it, we have already discussed this previously, that weight matrix is inverse of covariance matrix, or more appropriately the cofactor matrix. Fine. We know by the least square method. How do we apply it? As you can see over here, that phi is V transpose W V, and V, phi is a scalar here, okay, phi is a scalar, and these are the matrices. W is for weight, V is for residual, and we make this minimum. How do we handle it? We handle it by finding the partial derivative of phi with respect to residuals and equating to 0. This is how we make phi minimum. So that's the way we carry out the solution. Okay. What we'll do, we'll look into some examples in a moment. But if, depending our W, if our W is a weight matrix, if the observations are uncorrelated, okay, observations, we have the sets of observations and they are uncorrelated. There is no, all observations are totally independent, no correlation between them. If it is so, the W matrix will be a diagonal matrix and our least square solution appears like this, which we can further write as, so we are taking the weights into account here, W1 V1 square plus W2 V2 square plus so on, and Wn Vn square. And what we will try to do, we will try to make this minimum in our least square approach. Further, if the W, all the observations, you know, there may be situations when all the observations have been taken with the same weight. Okay, if we know that the weights are same, then in that case this W matrix will become an identity matrix. If it is so, we end up with that this phi is equal to sigma I varies from 1 to n Vi square, and we will try to make that minimum. Alright, and we can expand it further like this. Fine. Now one question over here. Since our high school days or even before that, we know that whenever we are taking any observation, we are taking the weight, okay, we have some chemical and we are weighing it. What we do, we weigh the chemical, let's say 20 times, and then finally now we have got 20 values, we take the arithmetic mean of that. We have been asked to measure, the length of a line. We measure it 100 times, 10 times, 30 times as desired, and we take the arithmetic mean of that. Now what is this arithmetic mean? Has it got any least square sense? Is it the best estimate? Okay, in the least square sense, that's a question. Something which we have been doing since our high school days. We straight away compute for any sets of observations. We straight away compute the arithmetic mean. So let's look at that now. Okay, now here in this, again we have a line, as you can see, the line is over here, and we want to take the observation of this line, and we have taken the observations as x1, x2 and x3. What we want to find the most probable value of this line, or we say the estimate of that line, okay, the adjusted value. This is what we want. How do we do it conventionally? We find the arithmetic mean. Arithmetic mean is x1 plus x2 plus x3 divided by 3, because we have got 3 observations. So we can find the arithmetic mean. But is this really the best estimate if we carry out the same problem by the least square? This is what we are going to check. Well, in the case of the least square, what we can do, as we always write, we can write here xi hat is xi plus vi. So what we are doing here, xi is observation, vi is the residual. So if we apply the residual on the observation, what we get the corresponding estimate. So we are getting the corresponding estimate here. Okay, so this thing can be written for all the observations, because over here the observations are x1, x2. So we can write it as x1 hat is x1 plus v1, x2 hat is x2 plus v2, x3 hat is x3 plus v3. We can write it like that. Now further, as you can see, I am bringing this vi on left hand side. So the right hand side becomes xi hat minus xi. Okay, xi hat minus xi. Now the least square, what is the least square? In the case of the least square, right now we are considering all the observations, x1, x2 and x3. All the observations have been taken with unit same weight. So there is no w here, no weight here. And then the least square says sigma of vi square, it should be minimum. So this is what we will try to do now. Now if sigma of vi square is minimum, what is sigma of vi square? Sigma of vi, our vi is over here, that's our vi, its value is xi hat minus xi. So we write it here, sigma of xi hat, I will write I for some time, then later on I will not use this I. We will talk about that why it is so. So sigma of xi hat minus xi square, this should be minimum. In order to make it minimum, what we need to do, we need to find the partial derivative of this phi with residuals and make them equal to 0. So let's do it now. To do it, because that's our, if you are doing it, so del by del xi of sigma xi hat over here minus xi square, this should be equal to 0. Now if you differentiate this with respect to xi, it becomes minus 2 sigma xi hat minus xi. Okay, so this should be equal to 0. Now please do it yourself also. Now this 2 is eliminated and we take this sigma inside, so we can write this as sigma of xi hat minus sigma xi is equal to 0. Now we had been using this this xi hat so far. However, because it's a single line, for each observation x1 hat, x2 hat, these are the, for each observation these are the estimates, x3 hat. So it's a one line there. So all these should be equal. So x1 hat should be equal to x2 hat should be equal to x3 hat, and this we are writing now as x hat. So if you are doing it for only 3 observations, what I can do here, I can write it as 3 times x hat. This minus, look at this, sigma xi is sum of all the observations. So x1 plus x2 plus x3, and that's equal to 0. Well, from here we can write that x hat, which is the estimate of this line from least square, is x1 plus x2 plus x3 divided by 3, and the same is also the arithmetic mean. So what we have proved here, we started with the concept of the least square. Okay, starting with that concept, we found the residuals. We made the sigma of sum of residual square. Okay, sum of residual square, we made it equal to the minimum, and in doing that, we arrive at the conclusion that the estimate or the best possible estimate that we can achieve for this set of observations by least square is same as the arithmetic mean. So if our observations are of same weight, that is important here, because we did not consider the weight here. Okay, our weight matrix was identity. If for all the observations, for example, the chemical that we are weighing, if we have weighed it 10 times, and all of these observations, whenever we are weighing, we are saying that, well, weight of the observation is same, the quality observation, precision of the observation is same. In that case, taking the arithmetic mean is same as carrying out the least square solution. Okay, let's look at another concept, that is redundancy and a model. What we do in the field, we always desire to get something in the field. For example, to determine the area of a rectangle, okay, to determine the length between 2 points, to determine angles between 2 points at an observation point. Okay, these are the things which are desired. To determine, for example, the shape of a triangle. These are the desired things. In order to achieve, realize this, what is desired, what we do, we carry out some observations. Now, in order to realize something which is desired, we can decide the way we carry out the observations in different way. Person A can carry out the observations in one scheme. Person B can carry out the observation in a different scheme. Person C can carry out the observation in a different scheme. Okay, so I will give you one example here. For example, let us say here is a length. We need to determine the estimate for this. What we can do, someone measures this length. Okay, let's say x1, x2, x3, x4, and he says, well, sum of all these will give me my final length. Someone decides to do it in such a way because the instruments that he has do not permit this kind of observation. So what he does, he takes a measurement of this length, which is, let's say, x1, and then he measures this one, x2. So these two persons, he has a different model and he also has a different model. Similarly, someone says, why to do these all observations? He does measurement of this length. I will show it by a different color. Okay, he measures this length. For example, if this is the length, he measures this length only once. For example, x1. Someone says, well, I will not take only a single measurement. I rather carry out multiple measurements, x1, x2, and x3. x1 is also this full measurement, x2 is also full measurement, and x3 is also full measurement. So what I am trying to say, in order to realize the desired thing, we can define the model in different way. Okay? Now, because our aim is that model will help us later on to adjust our observations. Further, in any model, we should have some redundancy that we have also seen. For example, here, in this triangle, the desired is to determine the shape of the triangle. We can determine the shape of this triangle only by observing theta 1 and theta 2, because the theta 3 can be realized by we can realize the theta 3 by this also. So the shape of the triangle is known. But here in this case, we don't have any redundancy in the object model. So before we begin our survey, okay, before we go to the field, we rely, or rather we try to plan it out. What will be our model for the competition? Whether our model will be able to have some redundancy, because the redundancy is required in order to eliminate the errors, or in order to have a check on the error. Whether it will be possible to carry out least square solution for our estimate, for our desired quantity, whether it is possible or not. Whether our observations, whether the way we have decided that we are going to take the observations will be able to fulfill our requirement. Okay, I will give you one example of that. Well, anyway, we will start by some notations. We write N naught. N naught is the minimum number of observations which are required to determine our selected model. Now here in this case, the minimum required is 2, N naught is 2, because if both observations are very correct, no errors, we can know the shape of the triangle. So the minimum required are 2 in this case. But if we have done, let us say theta 1, theta 2, and to include redundancy, we are doing theta 3 also. We have taken 3 observations. If this is the case, though the desired is 2, our number of observations is 3. We define the term redundancy as R is N minus N naught. That means the extra observations. We need only N naught observations to define our model, but we are taking N number of observations, extra observations. So 1 in this case, R is equal to 1, that's the redundancy in our model. This is also many times called degrees of freedom, okay, and will be more than 0. Now one more example here. Well, the idea is we want to fix location, size, and orientation of a triangle. These are the 3 things which we need to fix. Location, where it is located, its size, and its orientation. What all observations are required? The minimum number of observations. Let us say someone who went to the field has carried out theta 1, theta 2, theta 3, these 3 observations, as well as he has also observed the bearings of the lines. For example, here it is phi 1, phi 2, and phi 3. These are the bearings, as well as one has also observed the lengths L1, L2, and L3. But do we really need all these in order to determine, in order to fix the location, size, and the orientation of the triangle? What is the minimum required? Okay, so in this case, these are the observations. So what is the redundancy? In order to know the redundancy, we should know what is the minimum number of observations which are required in order to solve this problem, in order to fix this problem. Well, in this case, the minimum required, because we need to fix the location, size, and orientation. If I somehow can observe the coordinates x1, y1, x2, y2, x3, y3. Let us say somehow we have observed these coordinates. If it is done, the size of the triangle is fixed, the orientation of the triangle is fixed, and the location of triangle is also fixed. All these are fixed. So what we see only by 6 observations. So we will say our n naught is equal to 6. You can say this same problem in a different way also. The same triangle, well, I observe one value of phi, so orientation is fixed. I observe two angles, theta 1 and theta 2. I observe the length L1. What we have done so far? So far we have fixed the size of the triangle and the orientation of the triangle, but still the location of triangle is not fixed. To fix the location, we also observe x1 and y1. So these are again 6, x1, y1, theta 1, theta 2, phi and L1. Again n naught is equal to 6. So whichever way we go, we need minimum number of 6 observations in order to find the solution of this problem. The problem was to fix the location, size and orientation of the triangle. But the number of the observations that we had taken, the number of the observations were 9, or n was 9. So our redundancy R will be 3. So in any model, we can work out the redundancy like that. And this is important because we will make use of this later on. Okay, one final thing about this redundancy. As we saw that, we define a model, it should have proper redundancy because we want our observations with the redundancy. But not always. If there is redundancy, we can solve for the model. Now, I will give you one example here. Let's say again the aim is to determine the shape of this triangle. If this is the aim, well, we can do, because we have now taken the observations theta 1 and theta 2, and we need only these 2 observations in order to solve for this problem. But the solution will be unique, something which is not desired. Unique means we don't have any redundancy in the observations in this case. If only number of observations that we have taken is 2, okay, that's not desired. What we want to do, we want to have redundancy. Well, what we do, we also observe now theta 3. So now what we have done, we have increased the number of the observations, n is equal to 3, and now the redundancy is 1, that is n minus n naught. So we have a redundancy in our sets of observations, but can we solve for our model? Can we find the estimate of our desired quantity? No, still we can't find the best estimate for our desired quantity, because still for the shape of the triangle, this angle still needs to be determined from theta 1 and theta 2, because we don't have any observation here. So what do I mean? I mean, in this case, the desired cannot be achieved, cannot be computed. So not always a model can be solved even if the redundancy is more than 0. So this is important. Introducing redundancy in the observation is not the only thing. Rather, introducing the redundancy in such a way that the desired can be estimated is required. Now we will go for our approach for adjustment. We have 2 methods for carrying out this. We say the condition equation method and observation equation method. We will see them one by one, what these are. So first we will try to understand these. What is the concept of condition equation and what is the concept of observation equation? This is what we will try to understand now. Now, in the case of the condition equation method, it tries to frame conditions on the observations that we have carried out. Okay, it doesn't take the parameters of the model into account. Parameters means the desired things. Okay, for example, if you are observing a length of line, as you can see here, a length is there and we want to observe its length. So a parameter is x hat. Okay, that's the desired thing that we want to determine. So we don't take this into account, rather we frame our condition equations using the observations. How we can do? Now here in this case, let us say we have taken two observations, x1 and x2. This was measured once, x1, one measurement, and then another measurement of the same line, x2. So our n, that is number of observations, is equal to 2. How many observations we need in order to find that unique value of that length of the line? Only one observation. Of course, in that case, there will not be any redundancy. But that's the minimum one which is required to find the solution. So we say n naught is equal to 1. Only one observation. So the redundancy is 1. Now here it is important. What is the redundancy in the model? We can write the equal number of condition equations using our observations. Now here r is equal to 1, so we need to write one condition equation, and that condition equation will take into account only the observations. How do we write this? We write it this way. Well, let's get into it. What is the meaning of this? I am writing x1 hat is x2 hat. Obviously, x1 hat is x1 plus v1, x2 is x2 plus v2, x1 is an observation, x2 is also an observation, while v1 and v2 are the residuals. So once we apply this residual on x1, we get x1 hat, and similarly here we get x2 hat. So in any observation, if we are applying that residual, we are getting the estimate of that observation, and all these estimates should be same, because finally it should give me the line, the actual line. Okay, so all these x1 hat should be equal to x2 hat, means that is equal to x hat. So our condition equation in this case is x1 hat is equal to x2 hat. So what we have done in this condition equation, we have framed and one condition equation because our r was equal to 1. So we can frame one, again this is important, one independent condition equation. In a large problem, it may be possible that we may frame some condition equations which are dependent on the previous ones. So it should not be so. All the condition equations should be independent. So that's the condition equation that we have framed. So similarly, we can frame the condition equations for more complex problem. I am taking one example here. Again, the example is same. Starting from a benchmark, we are carrying out the labeling in order to determine the RLs of various points. Let us say the points for which we need to determine the RLs are point number 1, point number 2, and point number 3. We want to determine the RLs of these points. So what we do is, starting from the benchmark which is known, I take an observation along this route, and the value of the difference in RLs is L1. So by that I can determine RL of point 1. So this is a unique solution. We don't want it that way. Well, further, because we have to determine RLs for 3 points, I can go further to point 2 by observing this L2, then one redundant observation L3, because now this L2 can be computed. L2 can be computed through this route as well as this route. So we have introduced the redundancy in the observation. Further, in order to determine the RL of point 3, having known the RL of point 2, I am finding the difference in elevation between these 2 points, that is L5. So I can determine the RL of point 3 also. But I am also taking one more observation here, that is L4. So again there is redundancy. So what all observations that we have carried out? We have carried out L1, L2, L3, L4 and L5. These are differences in elevations, while the desired are relative elevations, okay, RLs of point 1, 2, 3. Let us write them as x1, x2 and x3. So the RL of these points are x1, x2 and x3. This is the desired thing, while we have carried out L1, L2, L3, L4 and L5 observations. Now what we will do, we will try to analyze this problem now. For this problem, number 1, what is the minimum number of observations which are required in order to find x1, x2 and x3? Well, you can guess very easily. What we can do is, starting from the benchmark, I can take this route. I take the observation L1, so I know the RL of point 1. Similarly, starting from benchmark, I can take this route and determine L3. I can find the RL of point 2. And finally, I can take this route and determine the RL of point 3 by taking these observations. So this is the only 3 observations. We can carry out only 3 observations in order to solve this problem, but in a unique way. That is important. We need only 3 observations, yes, in order to solve this problem, but our solution is a unique solution. We do not know about errors. It's a unique solution, We have been talking about that, the significance of the redundancy. There is no redundancy in the observations in our model. Well, the actual number of observations that we have taken is 5. So the redundancy here in this case is 2, which is n minus n naught. That's the redundancy. So what we will have? We should have 2 number of condition equations which are independent. So we need to write those condition equations now. How do we write it? Well, the condition equations can be written now as, if you look first in loop here, start from benchmark, go to point 1, go to point 2 and again go back to benchmark. So here is a loop. Here is a loop means we are starting from the benchmark, going to point 1, going to point 2 and again coming back to the benchmark. And what we are observing? We are observing the difference in elevation. L1 is difference in elevation between benchmark and the point 1. L2 is difference in elevation between point 1 and point 2. And L3 is difference in elevation between point 2 and the benchmark. It's a closed loop. So what we can do, using this closed loop, we can write one condition equation. And that condition equation will look like L1 hat plus L2 hat minus L3 is equal to 0. Now please mind it, I have put a arrow here. That arrow shows that this is the direction, or this is the positive observation. Okay, this is the positive observation, this is the positive observation. So the sign, this is why I have used minus here. Further, we have another loop, and in this loop, if we start from the benchmark, go to point 2, then come back through point 3 to benchmark. We can write for this loop as L3 hat minus L5 hat minus L4 hat. This is equal to 0. So what we have done, these are 2 independent condition equations. So the condition equations basically have a form of because these are the conditional equations. This is a matrix notation here. It's a function of the adjusted observations, okay, the estimates. That's why we are using L hat here. And the relationship between adjusted observations, whatever all the possible relations which are there and which are independent, we write them in this form. So these are the condition equations. So later on, we'll make use of these condition equations in order to find the solution by least square. Now here in this case, once using our solution of these equations, we'll have a method in order to solve for this equation or for these two equations, so that we can find L1 hat, L2 hat, L3 hat, L3 hat and L4 hat and L5 hat. So once these are known, means L1 hat, L2 hat, L3 hat, L4 hat and L5 hat, these are known. That means we have now the adjusted values of these. If you write, for example, L1 plus L2 minus L3, that will not be equal to 0, we know it, because these are the observations. But for L1 hat plus L2 hat minus L3 hat, that will be equal to 0 because these are the estimates. Once we know the estimates, what we can do, we can find the value of desired quantity. So what is the desired quantity? For example, the x1. x1 is the RL of this point. This is benchmark plus L1 hat. Similarly, the x2 could be benchmark plus L1 hat plus L2 hat. And x2 can be also written as benchmark, RL of benchmark plus L3 hat. Now in this case, these two x2 will be same, because in our least square solution, this functional model has been taken into account. So whatever the way we find the value of x2, both the values should be same if our solution is correct. Okay. So similarly, we can also determine x3 as benchmark plus L4 hat. So our desired quantities can be now computed if we know these estimates. So this is the method of condition equation. Now we will see the method of observation equation. Okay, now we are going for the observation equation method. In the case of the condition equation method, we saw that we frame the condition equations using estimates of the observations. Okay, for example, the L1 hat, L2 hat, L3 hat that we have seen. Only estimates of observations were taken into account, and we tried to write R number of, R means the redundancy, independent condition equations, and then we solve for them in order to determine the value of estimates of the observations, and then we find the desired quantity. Now here in the observation equation method, it is different. Here in this case, we include the estimates of the observations, yes, but in addition we also include the model parameters, means the desired quantities. What is the desired quantity? We also include that in the equation here. Now how we do it? Let's say it. We have a line over here and we want to observe this line. So the desired quantity is x hat. What we do, we carry out two observations, x1 and x2. Someone measured this line x1 and then again x2. Two observations have been taken. Now we know now U here comes for the number of unknowns in terms of the desired quantity. So the desired quantity here is the length of the line. So here is one unknown. So u is equal to 1, and not as in the previous case the minimum number of observations which can determine this unknown, and the actual number of observations which are actually taken. R is the redundancy. Now here in this case, the total number of observation equations that we can write is equal to C. C means R plus U. Over here in this example, C is equal to 2, because we are including the model parameters also into the our computation process in our least square solution or in writing these observation equations. So we will need to write C number of observation equations. Now how do we do it, particularly now in this example? We know x hat is x1 plus u. Okay, this is equal to x1 hat also. We can write, because we know for this problem x1 hat and x2 hat, these two are same obviously, which are equal to x hat. So x hat is our unknown. This is the only unknown. What we have done, we have taken these as observations. So what we are doing, we are relating unknown with the estimate of the observation. Okay, so how we can relate it? We can write one equation as we have written over here. X hat is equal to x1 hat, x hat is equal to x2 hat. This is how we can write, and x1 hat is x1 plus v1, x2 hat is x2 plus v2. Okay, so these are the two observation equations which we are able to form. They are independent observation equations. They are relating, important thing is that they are relating the unknown with estimate of the observation. So generally this will be the form of our observation equations. Now we look in the same example which we had done earlier. Now in this example we know the desired quantities are x1, x2 and x3. Okay, desired quantities, and we have carried out the observations L1, L2, L3 and L4, which we know these are the observations which have been carried out. Now what are the model parameters? The unknowns. The unknowns are the final estimates of x1, x2 and x3. Okay, so the total number of unknowns in this problem are 3, and not means 3, we have seen it before, n in this case is 5, so r is 2. So the C will be r plus u, so that is equal to 5. What is the meaning of this? The meaning is, if we are including these parameters also into the equations along with the estimates of observations, we will need to write 5 observation equations in this case. What these observation equations will be? The observation equations I have written over here. First observation equation, x1 hat. Okay, I am writing hat here because that is the estimate of this, is benchmark plus L1 hat. Okay, because it is relating the parameter with the estimate of the observation. Similarly, we can write one more also, and finally, and all these observation equations are, it is important, these are independent. This is important. Whenever we have a problem, we are going to solve a problem, we must ensure that the observation equations which we are writing should be equal to first the C, and all these should be independent. Once we have written these observation equations, we will apply the least square solution to these, and we have a method by the least square when we can find the solution of these equations. And through that solution, as is obvious, we will find the values of the model parameters as well as we will find the values of the estimates of observations. So what we will determine? By applying the least square, we will find the desired quantities as well as L1 hat, L2 hat, L3 hat, L4 hat, L5 hat. Of course, these are not really the desired thing. We don't need them, but well, these are computed in between. Our desired quantities are the ones which are actually being computed here. So our effort will be to determine these desired quantities finally. So what we saw today, we saw again the concept of the least square, then the criterion, how do we go about the least square, then the redundancy of a model, why it is important, why it should be there. We also saw one important thing, even if there is redundancy, it is sometimes so that the model cannot be solved. So whenever we are planning the survey, we should ensure that the model or the observations are defined in such a way that we can have the redundancy in the observations as well as we can solve for the desired quantities. Then we saw two methods or two approaches of condition equation and observation equation. We can form the condition equations using the estimates of observations, and the number of the condition equations are equal to the redundancy. Then in the observation equation, not only the estimates of observations, we also include here parameters of the model, the unknowns, the desired quantities. And the number of the equations in this case was redundancy R plus U, number of the unknowns. So we need to write that many number of unknown equations. So we just have an idea of condition equation and observation equation now. Next what we will do, we will frame further these equations for some example and we will try to solve it by the least square. So we will see the least square solution in these two approaches. Thank you.